the enumeration group is not there yet.
They're all outside.
There was a group of mathematicians that went to mannequin, and I think they. Okay, maybe they missed the first part. I think that talk will be better than the pancakes. Okay, it's my great pleasure to introduce Irving from Stanford.
University of Texas.
From University of Texas, who will be speaking about counting z-disks in the CP2 to
punctured
CP2.
All right, well, thank you for the invitation to speak. So today, I want to tell you about something that doesn't really have anything to do with homologies or physics, I guess a little bit about knots. But it has some cute number theory in it, of which I'm unreasonably proud. And so that's actually what I want to talk to you about today. So the project is about counting z-disks in punctured CP2, and this is joint with Anthony Conway and Maggie. Okay, so well, firstly, what is the project about? So let me just remind you of a very standard and now well-used theorem. So what I want to study is topological disks. So I study topologically sliced knots. And we will restrict to the simplest situation where I have a topological sliced disk whose complement has fundamental group Z. So such a thing we call a Z-disks. And it's a standard theorem that if I have any two Z-disks for the same knot in B4, then those two Z-disks are topologically isotopic to each other, rel boundary. Okay? So the usage of this theorem in the last few years has mostly been in coming up with examples of exotic phenomena, exotic pairs of disks. That's to say, this theorem allows you to conclude in an abstract way that if I have two disks which are both fundamental complement Z for the same knot, then they're topologically isotopic to each other rel boundary. But often there's some reason that you know that they're not smoothly isotopic to each other rel boundary. And people like this phenomena. They call it an exotic pair of disks. So here I've drawn for you one example. This example I first learned about in a paper of Kyle Hayden, although I think perhaps it was known to Aquilute. So I've drawn for you a particular complicated knot here. And this knot is in fact a slice knot, smoothly slice. And you can get two different smooth disks for this knot by compressing along the indicated red and blue curves of this genus 1 ciphered surface for the knot. These gives you two slice disks for this knot, and you can check that they both have fundamental group Z. Okay, and so by the aforementioned theorem, you know abstractly that these disks are topologically isotopic rel boundary, and yet there's some machinery that tells you they're not smoothly isotopic rel boundary. For example, Kovanov homology, knot-Floer homology, things like this. And so people like studying this kind of phenomenon. Okay, but it relies on this sort of topological classification theorem that tells you the two disks are topologically isotopic. Okay, so given the theorem, it's quite natural to ask, well, what about sliced disks or Z-disks in other manifolds other than B4? So I have, let's say, a 4 manifold, a smooth 4 manifold with boundary S3. I have in that boundary a knot. Let's say the knot is sliced in that 4 manifold. If I have a bunch of Z-disks for that knot, are they topologically isotopic to each other? Right? So a lot of people have worked on this question, Conway, Powell, Picarillo, and a lot is known. So I've put sort of the state of the art on the board for you. I'm not actually going to talk very much about this theorem, but I want to sort of clarify that this isn't by any means, I'm not claiming this is a new question or this is the first advance in such a question. Lots of people naturally study this question. And the point is there is some sort of abstract classification result. If I give you a manifold and a knot in the boundary, and I ask you, well, enumerate for me the topological isotopy classes of Z-disks for that knot. There is sort of a general framework by which this can be done, but it's sort of an abstract framework. And what I actually want to talk to you about today is, fine, let's just take a very simple example. Let's just take punctured CP2. Okay. If I give you a small knot, let's say like the trefoil or the figure eight, or something very simple, in the boundary of punctured CP2, and I ask for you how many topological isotopy classes of Z disks are there. Can I just tell you what they are? Can I enumerate them for you? Okay, and of course, underlying this point is that finding Z disks, finding a knot which has Z disks in B4 is a little bit of a slightly subtle thing, right? You have to have a knot with Alexander polynomial 1. So, of course, you can construct the knot in such a way by taking, let's say, a Whitehead double, but, sort of in nature without explicitly constructing it. It's not like they sort of, you look at the first few knots in the knot table and you say, oh, there's an obvious one. In contrast, it's not very hard to see, I'll say in just a moment, that there are a huge number of knots which are Z-slice inside of CP2. For example, the trefoil of the correct handedness, the figure 8. These are Z-slice in CP2. So you could say, well, okay, given the previous classification result that any pair of Z disks for a knot are topologically isotopic in B4, what about these simple examples? Wouldn't it be nice if, for example, I could find an exotic pair of slice disks for a simple knot such as the figure 8 inside punctured CP2? Okay, so that's sort of,
so
yes?
Can you explain to me this statement? Or
what is the statement? Okay, I will explain it even though I'm not going to talk about it ever again.
The automorphism with the branch fit form on mod out?
That's right. So if I have a knot, which is Z-slice inside of CP2, well, there are various data associated to this situation. I can, of course, take the infinite cyclic cover of the knot, and on this infinite cyclic cover, the first homology of this infinite cyclic cover, I have the Blanchfield form. If the knot, I can also take the infinite cyclic cover over the disk, right? And that on this form manifold, there will be the analog of the intersection form, the equivariant intersection form. And it turns out that the automorphism group of the intersection form, equivariant intersection form, will act on the automorphism group of the Blanchfield pairing, okay? And so the theorem is that if I fix the equivariant intersection form, there could be, many such Z disks that have that equivariant intersection form. Then the number of such things is this quotient. Okay. All right. So I told you that. I told you that there are many knots which are Z-slice and CP2 punctured. Why is that? Well, it's very easy to see that if I have a knot and I can do a crossing change of the appropriate sign to get to a slice knot, or even more loosely to get to an Alexander polynomial 1 knot, then such a knot is topologically Z-slice inside of CP2. Okay? And in fact, so the first theorem that I want to quote for you is that in fact every Z disk for a knot inside of punctured CP2 arises in such a manner. Okay? Every Z disk is topologically isotopic rel boundary to a Z disk which is obtained by doing a crossing change in a knot to an Alexander polynomial 1 knot. And I'll say more specifically this crossing change disk. If you're not familiar with it, I'll say explicitly what it is in a few slides. Okay? And in fact, how many, if I give you a knot, can I explicitly say how many Z disks are there? Topological isotopy classes of Z disks are there. And in fact, we managed to enumerate them explicitly in the simplest cases of the knot. Okay, so if the knot has trivial or quadratic Alexander polynomial, then in fact we perform an explicit enumeration, and it turns out that up to topological isotopy rel boundary, you bound 0, 1, 2, or 4, or infinitely many Z disks, depending on what exactly the Alexander polynomial is, which is a little bit strange. So in fact, what I want to talk to you about today is sort of this explicit calculation and this enumeration. Okay. All right. Maybe before I talk about the actual theorems, I want to say a little bit more about the motivation for the project, as I said at the beginning about the exotic pairs of disks. Okay. So. So I said at the beginning, the way you can use such a classification result is in conjunction with some other technique for distinguishing pairs of disks in the smooth category. There are many ways to distinguish pairs of disks in the smooth category. So for example, you can use Kovanov homology. This was work by Hayden and Sundberg. You can use knot floor homology. So this was work by myself, Abhishek Malik, and Matt Stoffrigan, sort of following work by Juhas, Miller, and Zemke, who use knot floor homology to distinguish exotic higher genus surfaces. So there are many of these, I'm going to talk about a strategy for distinguishing exotic pairs of disks, the strategy by myself and Abhishek and Matt. What is this strategy? Okay, so the strategy is that in order to come up with exotic pairs of disks for a knot, we will in fact focus on knots that are symmetric. Okay? And what we're going to do is we're going to try to understand the action of the symmetry of the knot on the knot floor homology of the knot. Okay? Now, why is this helpful? So let me go back to the example that I put on the first slide of this knot with this mysterious pair of disks here. So you notice that sort of the disks are obviously, the compressing curves that I've drawn for you in the genus 1 surface are obviously related by symmetry of the knot. Okay? So the disks inside of B4 for this knot are related by an involution of B4, which interchanges the pair of disks. And actually, what we proved, so this is a reproof of Hayden's result that these pairs of disks are not smoothly isotopic real boundary, they constitute an exotic pair. We actually use knot floor homology to show that any pair of sliced disks for this knot which are symmetric, which are related by sort of this obvious involution of B4, they necessarily are not smoothly isotopic to each other real boundary. Okay, so in particular, this pair of interesting disks is not smoothly isotopic real boundary, but in fact, any pair of symmetric disks for this knot are not smoothly isotopic real boundary. Okay? How do we sort of show this? Okay, well, as I said before, the proof proceeds by looking at the knot floor homology of the knot and analyzing the action of the symmetry tau on the knot floor homology of the knot. Now, the point is somehow that let's imagine that I had a sliced disk for this knot that was perfectly symmetric. Okay? So this sliced disk induces, because of the TQFT properties of knot floor homology, a map from the knot floor homology of the unknot to the knot floor homology of my knot. Okay? And in fact, I also know that this map is sort of equivariant with respect to the symmetry action. Okay? And so if I calculate the symmetry action on the knot floor homology of my knot, and I think very hard, and somehow I conclude that there's no possible equivariant map from the unknot to the knot floor homology of my knot, then I conclude that my knot cannot have any equivariant sliced disk. Okay? But actually, knot floor homology has this property that it is invariant if I have a knot concordance, and I wiggle the concordance by an isotopy real boundary, then the knot floor homology map is unchanged. So it turns out that actually what I've shown is not just that there cannot be a single sliced disk which is perfectly equivariant, but in fact I can't have any pair of sliced disks which are related by a symmetry and isotopic to each other real boundary. Okay? Okay, so you might say, what does this have to do with anything else that I've previously told you? Okay? So the point is that you should imagine that actually this is sort of a generic property of a knot. There are lots and lots of slice knots which can shown to be not sort of quote unquote equivariantly isotopy equivariantly sliced in this manner. So what I'm telling you is, for example, you can take a knot like the stevedore, you can take a knot like 946, and by analyzing the knot floor homology of this knot and the symmetry action on the knot floor homology of this knot, you can conclude that these knots do not have, they do not admit any pairs of sliced disks which are related by a symmetry but smoothly isotopic real boundary. Okay? So this is sort of a method for producing disks that are not isotopic real boundary. And what is the point? Well, the point is that, somehow, well, there are 2 points. Okay? So the 2 points are, one, that therefore, to produce an interesting example of exotica, the limiting factor is not like the invariant that tells you when the sliced disks are not smoothly isotopic. That's actually very common. Okay? The limiting factor is somehow finding like the interesting topological example, e.g., for example, an example of a knot which is smoothly, like the knot at the beginning. You want a knot for which you know that your 2 disks are necessarily topologically isotopic real boundary. Okay, so that's the first sort of claim. The claim is that the smooth obstruction is actually very common. Okay, the second observation is again Well, what is good about something like knot-floor homology? Well, the sort of broad strategy I told you about knot-floor homology just now isn't really specific to the disks being inside B4. If you know a little bit about knot-floor homology, then you know that knot-floor homology, due to work of many authors, has a sort of complete functoriality package. So knot-floor homology has cobordism maps for cobordisms that are not just in B4. And quite often, if you're careful enough, then sort of various things like, sliceness obstructions, genus obstructions, they hold in things not just B4, but, things like, definite manifolds, things like that. So you could sort of hope that if you're careful enough about the formalism, this strategy that I told you before about, saying that often, symmetric knots, you have these pairs of disks which are not smoothly isotopic roll boundary, that obstruction is sustained when I talk about the sliceness of those knots, not just in B4, but in the manifolds such as CP2 punctured. Okay? So that was the sort of motivation for studying this question, at least on my end. Okay? And in fact, the strategy in some sense does work. So for example, I told you the figure 8 is Z slice in CP2. You can in fact construct pairs of slice disks for the figure 8 in CP2, Z slice disks, which are distinguished by their maps on knot-floor homology. Symmetric pairs of disks, which necessarily are not smoothly isotopic rail boundary. Okay? So that part of the program is sustained. Okay? Unfortunately, when you actually go do the calculation for the enumeration of topological isotopy classes of Z disks for the figure 8, it turns out that the figure 8 has 2. Okay? So unlike for slice disks in B4, where there's only 1, the figure 8 has exactly 2 Z classes of topological Z slice disks. And so all you've done is you've realized both of those classes smoothly. So that was kind of a disappointment. And unfortunately, we haven't so far been able to find any new interesting examples of exotica. So that was sort of a long detour into my motivation for this question. So now let me tell you about the actual theorems at the beginning and explain a little bit about what's going on. Okay? Are there any questions before I continue? Okay. All right. So let me sort of say more precisely what I mean by a crossing change disk. Okay. So I told you that if I have a knot and I can do a crossing change to an Alexander polynomial 1 knot, then that knot is Z slice inside of CP2. Okay. So more precisely, I'll say that J is obtained from K by positive generalized crossing change along some curve gamma if I do -1 surgery on gamma. And upon identifying -1 surgery on this curve gamma with S3, I get the knot J. Okay, so here gamma is an unknotted oriented curve with 0 algebraic linking with K. Okay? And so suppose that K admits such a crossing change curve to an Alexander polynomial 1 knot J, then I claim that we obtain an associated crossing change disk, which I'll denote by D sub gamma, inside of CP2. Okay? And what is the construction of this crossing change disk? So I want to be a little bit careful, actually. Okay, so I want to start off with the fixed model for punctured CP2, and the fixed model for punctured CP2 is the following. I just take S3 cross I, okay? And on the outgoing boundary of S3 cross I fix an unknotted curve C, an oriented unknotted curve C. And along this oriented unknotted curve C, I do a -1 frame two-handle attachment. Okay? The reason it's -1 is because actually I'm going to reverse orientation on the whole thing to make it CP2. Okay? But let's not worry about the orientation too much for now. Okay? So I do, I have this fixed model. I have this fixed curve in S3 cross 1, which I do -1 frame two-handle attachment along. And of course, I cap the whole thing off with B4. And now I've made, with some orientation, CP2. Okay? So now suppose that I have a knot, here I've done the trefoil, and I pick for you an unknotting curve to an Alexander polynomial 1 knot, or in fact, perhaps an actual slice knot or an unknot. Okay, so here the K is in the incoming copy S3 cross 0. I have this curve gamma, which is represented by the green curve. Okay, and then I just take an ambient isotopy. I take the trace of an ambient isotopy where the green curve is moved into the fixed curve C on the outgoing boundary. Okay, and then bang, when I attach the two-handle, of course, in the model after I've attached the two-handle, the outgoing S3, now I have an Alexander polynomial 1 knot, and I can cap that off with a topological Z disk in B4. Okay? I'm being very careful with the statement because I want to consider all of my disks as sort of living in the same copy of CP2. Okay? I don't want to, when I compare a pair of disks, I don't want to do some strange reparameterization of the boundary, right? So, every choice of unknotting curve for K, and I think of K as being fixed in the incoming boundary of S3 cross I, allows me to define a disk in this manner by doing this isotopy, which moves my unknotting curve into C, and then capping off with a Z disk. Okay? And what you can show is that it doesn't matter what isotopy you choose to take your unknotting curve gamma into C. It doesn't matter up to, for the purpose of topological isotopy real boundary, it doesn't matter what you cap off by. What is not entirely obvious is that, in fact, in the story, the curve gamma and the curve C have to be oriented. Okay? And actually, the disk that you make does depend on whether in your isotopy you move your curve gamma to C sort of with matched orientation, or you could imagine right before I move gamma to C, I flip gamma 180 degrees and it moves into C, with reversed orientation. I could also cap that procedure off with a Z-slice disk. That does not necessarily give you the same topological isotopy class of disk. Okay, so the orientation of gamma and C are important, and I'll say more about this in a couple of slides. Okay, so this is the definition of a crossing change disk associated to a crossing change curve gamma. And the first assertion that I make to you is that every Z disk for a knot K is topologically isotopic real boundary to such a thing. Okay? So you say fine. Okay? Very well. So suppose I give you two disks which are constructed in this manner. How do I know when they are topologically isotopic real boundary? Okay? Well, that's actually very straightforward. So if I have both of the curves, unknotting curves gamma 1 and gamma 2, remember these are sitting in the same, these are curves in the same copy of S3, Well, what I do is I just take these two curves and I lift them to the infinite cyclic cover and I look at their homology classes. And if the two curves are the same up to multiplication by K, the two disks are topologically isotopic real boundary. And this is an if and only if statement. Okay, so this is a totally explicit enumeration of the set of Z-slice disks for not up to topological isotopy real boundary. Okay? Explicit in a sort of a topologically constructive sense, so then you can say, well, fine. So can you be even more, algebraically, can you give me the count of such things? Okay? So, well, then you say fine. Okay, so basically the Z disks are classified by the lifts of these curves. Not every class in the first homology of the infinite cyclic cover arises as the lift of such a crossing change curve to an Alexander polynomial 1 knot. Okay, and in fact, this is something which is well studied. So it essentially follows by work of Borodzik and Friedel that the set of curves which you get in this manner is the set of generators of the first homology of the infinite cyclic cover, which satisfy this equation that the self-Blanchfield pairing of the knot is equal to 1 over the Alexander polynomial.
Actually, this is a result of Fogel from 1993.
Okay, fine. My citation is overly generous, perhaps, but okay. So let me, so if you, probably several people in the audience know it, but if you've never seen the Blanchfield pairing before, this is basically the analog of sort of the rational linking pairing for a rational homology sphere. So if you take the infinite cyclic cover of the knot, then on the first homology you sort of have an equivariant rational pairing, rational linking form. That's what the Blanchfield form is. Okay, it's not really that important exactly what it is. Okay. Now you say fine. Then that means I just have to look at the first homology of the infinite cyclic to enumerate the number of Z disks. I just look at the infinite cyclic cover of my knot, and I enumerate this set. Okay. So fine. So now this is like a totally algebraic problem. How do I just enumerate the elements of this set? Okay. Okay, fine. So firstly, what is the first homology of the infinite cyclic cover of the knot? Well, in fact, in this case, it's very, very simple, and the reason is because if you presuppose that the knot is Z-slice in CP2, okay, then the infinite cyclic cover of the knot is the boundary of the infinite cyclic cover of the disk, okay? And if the disk is inside punctured CP2, then you can convince yourself that the second homology of the infinite cyclic cover of the disk is Z adjoint TT inverse. Okay? And basically what that means is it's just like if I gave you, a two-handle attachment diagram, presenting a four-manifold whose boundary was as a rational homology sphere. The first homology of the rational homology sphere, is the co-kernel of the intersection form of my four-manifold. Okay? So what happens is that the first homology of the infinite cyclic cover is presented as the co-kernel of, in this case, a one by one matrix. Okay? And since you know what the order of the first homology is, you immediately know that the first homology of the infinite cyclic cover has to be this very simple thing, ZTT inverse modulo the Alexander polynomial. Okay? Okay, fine. So then what you observe is that, you stare at this set which you are trying to enumerate. Okay? And what you realize is that the set which you are trying to enumerate is not very hard to show using the fact that the Blanchfield pairing is sesquilinear. That the so-called set of unitary units acts freely and transitively on the set that you want to enumerate. Okay? So the set of unitary units is the set of things inside this ZTT inverse modulo the Alexander polynomial. The set of such things such that P of t times P of t inverse is congruent to 1 modulo the Alexander polynomial. Okay, and because the Blanchfield form is sesquilinear, if I take any such P and I multiply it by both entries here, then of course I don't change the Blanchfield pairing. Okay? So in fact now I've made it into a totally algebraic question, which is that in order to enumerate the set of Z disks for a knot, I just have to figure out the cardinality of the set of unitary units inside this strange quotient polynomial ring, ZTT inverse modulo the Alexander polynomial. Okay? So that is the algebraic upshot of the classification theorem. Okay? So here I just stated again. So the set of Z disks is in bijection. With this set of unitary units, UN, okay, modulo, remember I told you that the curves are allowed to be equal up to multiplication by t to the k. Okay, so what I have to do is I have to calculate the cardinality of the set of unitary units modulo this subgroup of unitary units which are just given by powers of t inside this polynomial ring. Okay? Are there any questions? I know it's right after lunch, so everybody's sleepy. So, all right. And so what is the outcome? Okay, so the outcome is that if you have this knot, let's say the knot is quadratic Alexander polynomial, and the knot is Z slice in CP2, then as I said, it bounds 1, 2, 4, or infinitely many Z disks up to topological isotopy REL boundary. Okay? And here is the actual casework. Okay? If the Alexander polynomial of the knot is either trivial, or it is the Alexander polynomial of the trefoil, then it bounds a unique Z disk up to topological isotopy REL boundary in CP2. If it has the Alexander polynomial of the figure 8, the Alexander polynomial of the stevedore, or it has the Alexander polynomial delta n up there, where n is negative a prime power and with odd exponent, then it bounds 2 topological classes up to topological isotopy REL boundary. Okay? If the leading coefficient is negative p to the k for k even, then it bounds 4. And in every other case, it bounds infinitely many Z disks up to topological isotopy REL boundary. Okay? So that's the enumeration. And actually, for the rest of the talk, what I want to tell you is where the enumeration comes from, because is that not the purpose of mathematics to explain the numerology? All right, so what I want you to sort of notice is that really, outside of like a handful of cases, the number of Z disks is finite if the leading coefficient is negative a prime power, and it's infinite otherwise. Is basically, roughly speaking, the casework. Okay. So, how do you actually perform such a calculation? Okay, so this is the part where I ask you to recall basic number theory. I gave this talk in front of an audience of gauge theorists, and I was quite sure that they didn't recall the basic number theory, and so I was able to make this joke. But if people in the audience do recall the basic number theory, please just play along until the end of the talk, okay? So, all right. Let's just consider the very simplest cases of the Alexander polynomial of the trefoil and the Alexander polynomial of the figure 8. Okay, so remember, what I've told you is I'm just supposed to understand this ring, ZTT inverse modulo the Alexander polynomial. Okay? I'm supposed to understand the units in this ring. I'm supposed to then understand this unitary units in this ring, and then I'm supposed to quotient out by the subgroup T to the K, and I'm supposed to count the number of elements that I get. Okay? That was the procedure. Okay? So first, let's say, do we understand this ring? Okay, so we look at this ring and say, okay, this is very easy. This is just, like undergraduate stuff. I mean, this quotient ZTT inverse modulo the Alexander polynomial is the same thing as adjoining the roots of this polynomial here, the roots of this polynomial, of course, the sixth root of unity, zeta. Okay, so this polynomial quotient ring is just Z adjoin the sixth root of unity. Notice that if I join the sixth root of unity, power of the sixth root of unity is also inverse of the sixth root of unity, so adjoining T inverse did nothing. Okay? So I have this isomorphism with T, of course, being sent to zeta. Okay? So at least I understand the ring. Okay? Likewise, what about the case n equals 1? Okay, well, the end case n equals 1, I again look up here, I say, okay, look, I mean, understanding the quotient polynomial ring is the same thing as just adjoining the root of this polynomial. The root of this polynomial is 3 plus or minus square root 5 over 2. Of course, adjoining 3 plus or minus the square root 5 over 2 is the same as adjoining 1 plus or minus the square root 5 over 2, for reasons which will be clear in just a moment, and say I like this 1 plus square root 5 over 2, this omega, slightly better. So this quotient polynomial ring is just Z adjoin omega, where omega is this irrational number here. In this case, you can check that the correspondence sends T to omega squared, okay? Because omega is not quite the root of this polynomial, okay? And notice that, the conjugation T goes to T inverse corresponds to negating the sign in front of the radical, okay, under this correspondence, okay? Okay, what is so good about making this identification? Well, we are very fond of these two rings. Hopefully you've seen them before. These two rings are the so-called rings of integers of these quadratic number fields, q adjoins square root minus 3 and q adjoins square root 5. Okay, so let me briefly jog your memory. So recall that if I have a field extension of the rational numbers, then the so-called ring of integers of that field extension is the set of things satisfying a monic polynomial with z coefficients, okay? And the point is, for whatever reason, people love studying these objects, and they're very well understood is the whole point. So I've identified the quotient polynomial with something I've claimed for you is very well understood, okay? In particular, this formula here tells you that the things z adjoin zeta and z adjoin omega are the so-called rings of quadratic integers for the quadratic number fields. Q adjoin root -3 and Q adjoin root 5, okay? And the point is that these are well studied and their units are understood, okay? So, for example, the first one, probably not very difficult. Z adjoin zeta, what are the units in Z adjoin zeta? Not very hard to see that it's just the cyclic subgroup generated by zeta, okay? So those are what the units are, okay? And what are the unitary units? So the unit, because T goes to T inverse corresponds with conjugation, it's not very hard to see that, every unit here is unitary, okay? But also, remember I told you that, so I have to enumerate the set of unitary units, so this is just the subgroup generated by zeta, but I have to quotient out by the subgroup generated by T, right? And under the identification, T mapped to zeta, so actually the quotient is trivial, okay? Analysis done for this trivial case, okay? What about the other case? Well, now you once again ask yourself, in this so-called ring of quadratic integers z adjoin omega, what are the units, okay? And now it's a slightly less trivial exercise / theorem that now there are actually many units in z adjoin omega. I have plus or minus 1. And in fact, omega turns out to be a unit, and every power of omega turns out to be a unit, okay? And in fact, omega is sort of not torsion. I mean, the powers of omega are all distinct, okay? So I sort of have this z2 cross z set of units inside of z omega. That's sort of a calculation, a standard calculation, standard theorem. And once again, you can check what are the unitary units, okay? And if you check what the unitary units are, if you do a quick calculation in your head, omega being 1 plus square root 5 over 2, then omega times omega bar is equal to minus 1, okay? So omega is not in fact a unitary unit. The unitary units are plus minus the even powers of omega. And if you remember, I also asserted to you that under the identification with the polynomial ring, t actually is sent to omega squared. Okay? So what happens is that when I quotient by the subgroup generated by powers of t, I just sort of have the plus minus 1 left over. And in this case, the enumeration gives me 2 elements, z mod 2. Okay, so this is, first case, the set of the case of the trefoil. The second case, the case of the figure 8. Okay? Are there any questions? So this is elementary number theory, okay, as indicated by the title of the slide. Okay, so now you say, well, fine. Okay, I mean, can't I just do this in every single case? Why don't I get some, what interesting numerology could there possibly be? So you say, okay, fine. Once again, let's suppose for simplicity that my Alexander polynomial is irreducible. Okay, so then you say, well, is my quotient polynomial ring the same as adjoining one of these sort of quadratic things? Okay, and unfortunately, it turns out that's not quite the same. Okay, so the simple observation is that the quotient polynomial ring I care about is isomorphic to z adjoin this quadratic thing, but then I also have to invert n. Okay, I have to join 1 over n, and why is that? Well, it's because if I actually look at the roots of the quadratic polynomial, the roots of this polynomial here, this quadratic polynomial, are what I've written on the board. You see, there's this annoying n in the denominator, okay, which is not sort of the thing that you get out of studying, quadratic number fields. Okay, so clearly, the roots of this polynomial are in this adjoining. If I join both chi and 1 over n, then I can get the roots of this polynomial. And conversely, it's not very hard to see that you can get both chi and 1 over n by joining both the 2 roots of the polynomial delta n. Okay, so the point is there's some slightly different identification, slightly more complicated, that the polynomial ring that I want to consider is not quite a quadratic ring of integers. It is a quadratic ring of integers adjoin 1 over n. Okay? So now you say, okay, so you might say, why was it so good that it was a quadratic ring of integers? Why do I care so much about, specifically thinking about this chi element here? Well, it's because the starting point is, as I told you, the unit group of a quadratic ring of integers is totally understood. Okay, so the point is that z adjoin chi, the unit group of z adjoin chi, is totally standard. Okay? And there's a famous theorem called the Dirichlet unit theorem, which tells you what the unit group of a quadratic number field is. So the case that I care about, suppose that the thing under the radical, so remember chi was 1 plus square root 4n plus 1 over 2. For simplicity, let me assume that the thing under the radical is square free. Okay? So the unit group of z adjoin chi, if the thing under the radical is positive, has rank 1. Okay? Just like in the case z adjoin omega, the unit group is known to be plus minus 1 cross z. Okay? So sometimes this is stated that if the radical is positive, then there exists a fundamental unit in z adjoin chi such that every other unit in z adjoin chi is is plus minus some power of the fundamental unit. Okay? This is like a sort of famous basic number theorem. Okay? In the other case, if the thing on the radical is negative, then the unit group is finite. And in fact, excepting in the case that at n equals minus 1, the unit group is plus or minus 1. Okay? So this is Dirichlet's unit theorem for quadratic number fields. If you know Dirichlet's unit theorem, then you know that this is actually the most trivial and silly case of Dirichlet's unit theorem. Nevertheless, it's what we are going to use today. Okay? So the point is, we know what the unit group of z adjoin chi is. Okay? It's basically rank 1 or rank 0, depending on whether or not the thing under the radical is positive or negative. Okay? So now you say, what I need to do is I need to bootstrap to understanding the units in this augmented ring, where I've now inverted n. Okay? So what are the new units in this new ring z adjoin 1 over n chi? Okay? Well, the bright observation is that, well, obviously n is now a unit. Okay? What other units are there? Well, every divisor of n is a unit, right? Because if n is equal to a times b, then a is a unit with inverse b over n. Okay? So every divisor of n is a unit, and in fact, every divisor of n to the k is a unit. Okay? And suppose that I make the simplifying assumption that z adjoin chi is a unique factorization domain. And I ask you, what are the units inside z adjoin 1 over n chi? Okay? Well, then the units are whatever I had before, together with, I calculate the prime factorization of n inside of z adjoin chi. Let's say the prime factorization, the prime factors are p1 through pn, and all of these are now units in z adjoin 1 over n chi. Okay, and it's not very hard to show that these are sort of multiplicatively linearly independent. Okay, so I have an explicit description of the unit group, which is predicated on whether or not z adjoin chi is rank 1 or rank 0, together with the prime factorization of n inside of z adjoin chi. Okay, so now we are getting closer and closer to a totally explicit calculation. Okay, so let me do an example for you on the board. Okay, so let's consider the n equals 3 case. So the n equals 3 case is I have a knot with this quadratic Alexander polynomial, okay? And I'm supposed to understand the units in this ring z adjoin 1 over 3, comma chi, where chi is this thing, 1 plus square root 4n plus 1 over 2, okay? So what am I supposed to do? Well, I'm supposed to firstly remember the prime remember that in this case, z adjoin, the part of the unit group coming from z adjoin chi is rank 1, and now I have to factor 3 inside of z adjoin chi. Okay? And if you think about it, if you look at it very hard, then you discover 3 is no longer prime in z adjoin chi. It factors into 2 things. Okay? In fact, it happens to factor into negative chi times chi conjugate. Okay? So what that tells you is that the unit group that I care about in this case is rank 3, 1 rank coming from this thing, and 2 ranks coming from the factorization, the prime factorization of 3 in z adjoin chi. Okay? Okay, so now, again, let's think back. So what we're supposed to do is we're supposed to understand the set of unitary units in this ring. Okay? And then I'm supposed to quotient out by the subgroup generated by t to the k. Okay? Now, what you can check is you can check that the things coming from z adjoin chi, they all have norm plus or minus 1. Okay, so they're either unitary units or sort of half of them are unitary units. Okay, the units chi and chi bar here are not unitary. Okay, the norms are not 1. However, the ratio of chi and chi bar is unitary. Okay, so the set of unitary units in this example has rank 2, 1 coming from the standard Dirichlet unit theorem, and the other coming from half the number of factors in the prime factorization of 3. Okay? And then, now, okay, fine. So you could say, okay, that's just an example. Okay, but it turns out that this is a very good example because, in fact, another nice number theory theorem comes to your rescue. And it tells you actually exactly how n factors inside of z adjoin chi. Okay? It turns out that, so before, n was 3, which was prime in z, and it factored into 2 factors, and in fact, this will always happen. Okay? So every prime factor of n will factor inside of z adjoin chi into 2 conjugate prime factors. Okay? That's, I'm going to call this the fake splitting criterion. Okay? Why it's the fake splitting criterion, I'll say in just a moment. Okay? But what that means is that the rank of the unitary units as a function of n is given by the following very straightforward thing. I add 1 if n is positive. That's the part coming from the Dirichlet unit theorem. And then I take I add the number, the rank is, I add to the rank the number of prime factors of n. Because according to the splitting criterion, inside of z adjoin chi, I will factor, for each prime factor of n and z, I get 2 prime factors which are conjugate in z adjoin chi, and the ratio of those will give me a unitary unit. Okay? And then what you can show is that accepting in the special case n equals minus 1, this mysterious rank 1, this t to the k will in fact span an infinite subgroup of un. It will span a rank 1 subgroup of un. So the rank of the set of z disks is just the thing that I've written on the board minus 1. Okay, because I quotient out by t to the k and I count. Okay, so you see that that is the thing which underlies the numerology about whether or not the number of z disks for a knot is infinite or it's finite, right? In order to be finite, okay, if I have negative a prime power, then of course there's only 1 prime divisor. So that's exactly when I get sort of the finite case. Okay, modulo the case like n equals 1 at the top. You don't count n equals 1 as having any number of prime divisors. Okay, are there any questions? Okay, now just like some very clean up things that I have to tell you. So, I mean, the strategy that I've told you actually has a lot of holes in it. So, for example, I assumed that the Alexander polynomial was irreducible. I assumed that the thing under the radical was square free. I assumed that z adjoint chi was a unique factorization domain, which is not actually true. So you have to take the argument and you have to patch it in a bunch of cases. Okay, that's actually why in the case of the stevedore, anything with the Alexander polynomial, the stevedore also has a finite number of z-disks, even though that's a case where n is greater than 0. Okay, I'm not really going to talk about sort of the patches necessary in the number theory, but if you have questions about it, you can ask me afterwards. Okay, so hopefully that's sort of, I don't know. I mean, I know people are somewhat tired having eaten lunch, but hopefully this was like a mildly cute diversion into having you remember number theory from the deep past. Okay, so let me now talk about some topology, some interesting phenomenology, and some questions. Okay. So I sort of am glossing over it, but you could say, well, in addition to asking about when two disks are the same up to isotopy REL boundary, topological isotopy REL boundary, you can ask about the equivalence relation where I concern myself with disks that are equivalent REL boundary. And what that means is that I want a self-homeomorphism of CP2, which is the identity on the boundary, which moves one disk into the other one. Okay? And it might not be obvious whether or not the two notions are the same. And in fact, they are not the same. Okay? In fact, in B4, they are the same. Okay? But in CP2, they are not. Okay? And it turns out that if I want to enumerate the set of disks up to equivalence REL boundary, then that is in fact in bijection with this slightly different quotient object here, un modulo plus minus t to the k, instead of just modulo t to the k. Okay? And what that basically tells you is that generically there are twice as many disks up to isotopy as there are up to equivalence. Okay? Somehow there's like a left, when I mod out by t to the k to count the number of disks up to isotopy, as long as plus and minus 1 are distinct inside of u to the n mod t to the k, there's sort of this leftover plus minus 1. And if I quotient by that, I get the number of disks up to equivalence, which will generally cut the number of disks in half. Okay? Except in very certain cases, for example, in n equals minus 1, it turns out that plus minus 1, they're the same elements in u to the n mod t to the k. Okay, so I don't reduce the number of disks. Okay, what is the sort of explanation of this discrepancy? Well, the explanation of this discrepancy is that if I have a disk inside of punctured CP2, well, there's a homeomorphism of CP2, which is the identity on the boundary, but is non-trivial on CP2. In fact, it's homologically non-trivial. It acts in multiplication by minus 1 on the homology of CP2. Okay, so certainly that homeomorphism of CP2 has no chance of, let's say, being topologically isotopic to the identity. Right? You could hope that, if I am studying equivalence versus isotopy of disks in B4, somehow I would say, well, maybe if I have a homeomorphism of B4, then REL boundary, it's topologically isotopic to the identity or something like that. That certainly cannot happen in this case, right? And so, in general, you could have a pair of disks. So, in fact, as I mentioned to you about the example of the figure 8, so indeed what happens is that the pair of disks, you can come up with a pair of disks for the figure 8, which are distinguished by their maps on Knopfler homology. But unfortunately, they are related by this homeomorphism of CP2, which is not the identity on the second homology. And so you might not think, there's no reason for the disks to be topologically isotopic REL boundary. Even, I do stress that, just because this is true does not mean the disks are not topologically isotopic REL boundary. In the case of the trefoil, for example, the disks are still magically topologically isotopic REL boundary, even though they're related by homeomorphism, which is not the identity on second homology. Okay? But unfortunately, in the figure 8, it turns out that you've just generated the two topological classes of disks. Okay? Indeed, and so unfortunately, the examples that we've tried so far sort of have this sort of defect, that the things that you can distinguish using the smooth invariants, unfortunately, they are precisely the ones that are related by a homomorphism of CP2, which does not appear to be topologically isotopic to the identity. So we probably don't expect that the disks are topologically the same. Okay, so let me just point out the sort of weirdness example of trefoil. So the point here is, that it turns out that, as you might guess, the sort of multiplication by -1 thing on the second homology turns out to be sort of the same thing as whether or not when I construct the disk, I move the curve gamma to C in an oriented fashion or a flipped oriented fashion. Okay? And so the trefoil has this particular property that this unnodding curve here with this orientation is actually smoothly isotopic to itself with reversed orientation. So it follows from that in this case, it doesn't matter which isotope I use to move gamma into C, whether I reverse orientation or not. I actually get the same disk up to smooth. In fact, up to smooth isotopy about boundary. Okay? Other questions? Well, okay, so I will say, I just want to give some examples of enumerating Z disks. Okay, so fine. So I said vaguely that some quadratic polynomials have 2 disks and some have 4 disks and blah blah blah. So I'm just going to draw for you an example of how this sort of thing helps you explicitly sort of draw the various disks in the enumerator. Okay, so let's just take the case of let me take a quadratic polynomial where the leading coefficient is negative a perfect square, okay? Which in particular includes some of the cases that I talked about earlier where the leading coefficient is negative a prime power with even exponents, okay? So in this case, you can actually always write down 4 particular unitary units, okay? The unitary units you write down are plus or minus 1, and then also plus or minus this linear polynomial kt minus k, okay? So you always have these 4 unitary units here, okay? And so the point is basically that I always have 4 z-slice disks if I can find algebraic unnodding curves which correspond in some sense to these 4 elements. Okay, so I'm going to just draw an example for you. Okay, so here is a twist knot, negative k squared twist knot, which has this Alexander polynomial. Okay, so here are some examples of unnodding curves. Well, here's an obvious one, gamma 1. Okay, so if I take this gamma 1 here, you remember the handedness, this is obviously an unnodding curve. Okay, so gamma 1 defines a z-slice disk, in fact a smooth z-slice disk, and minus gamma 1, in fact, confusingly defines a slightly different z-slice disk. Okay, so here's another unnodding, quote unquote, unnodding curve, gamma 2. Gamma 2 is not like a smooth unnodding curve, but it turns out that gamma 2 is a curve which takes this particular knot to an Alexander polynomial 1 knot. Okay, and the reason is, roughly speaking, is that here, the twist knot is in fact obviously a twisted Whitehead double. And it turns out that the gamma 2 is chosen such that when you blow down gamma 2, you get an untwisted Whitehead double of something. In fact, you get an untwisted Whitehead double of a particular torus knot. Okay, so this is supposed to indicate you got this thing here, and it turns out that this is untwisted. Okay, and so it has Alexander polynomial 1. Okay, so this curve gamma 2, and then what you do is you calculate, you look at gamma 1 and gamma 2, and you calculate their lifts to the infinite cyclic cover of the knot, and you can in fact discover that they're not the same. Okay, so in the case of, let's say, the negative k squared twist knot, these are in some sense realizations of the 4 topological classes of z-disk. Okay, plus minus gamma 1 and plus minus gamma 2. Okay, and you can do other sort of interesting examples with other nice families of knots that have various quadratic Alexander polynomials. Okay, so maybe I'll close with a question. As this example shows, so for this example. So these 4 disks actually exist whenever the coefficient of the Alexander polynomial is negative perfect square. It's just that the coefficient is negative even prime power, then these constitute all of the z-disks for the knot. So in this case, I've demonstrated two classes smoothly. And the two other classes, I haven't given you smooth representatives. Because for gamma 2, this is not a smooth, you don't get, this is not an actual unknotting curve. You go to an Alexander polynomial 1 knot, so you have to cap off by something that is not a priori a smooth disk. Okay? So an interesting question, which I have no idea how to answer, is that is there an example in which you can provably show that some of the Z classes, some of the topological isotopy classes of Z disks, some of them are realized smoothly and some of them are provably not realized smoothly. So in this case, two of them are realized smoothly. And it's not really obvious how to realize the other two of them smoothly. But I don't know how to prove that you can't realize them smoothly. Of course, in the case of Z disks inside of B4, there's only ever one topological isotopy class of disk. So of course there are examples in which something is topologically Z-sliced but not smoothly Z-sliced. But the question is, can you have an example where there are multiple classes of Z disk and the sort of smoothness realizability of the class depends on which of the Z disk classes you are choosing. Okay? All right, that is the end of the talk. So thank you very much. Are there any questions?
Okay, are there any questions? I have a question. So whenever you have this unknotting curve gamma, then it gives you a z-disk, and the z-disk is depends only on the homology class gamma represents in the Blanch field.
In the infinite cyclic cover, yes.
In the Alexander module. But the curve gamma, whenever you perform the surgery, the resulting knot after the generalizing unknotting move might depend actually not on gamma, but not on the class of gamma, but on the gamma in isotopy class of gamma in the complement of K.
Yes.
Can you get different smooth slice disks?
Can you get different smooth slice disks?
Smooth slice disk if you take different representatives of gamma in the Alexander module.
I mean, in principle, yes. So, for example, up to, everything I said was up to topological equivalence row boundary, or topological isotopy row. I should say that, the question where I asked at the beginning, can you find exotic disks inside of CP2? I do not mean to imply that it is not already, it is known already that there are exotic disks in CP2. Okay, the question is can you have a very simple example, right? To answer your question, for example, I could even take something, for example, I could take something which has a crossing change to the knot that I wrote at the beginning, right? The knot that I attributed to Kyle Hayden, and I could cap off with either one of those, either one of the disks for that knot, which were not smoothly isotopic row boundary. And you would expect perhaps that, that difference would be sustained, into the resulting two disks should not be smoothly isotopic row boundary. So you can certainly get different smooth isotopy classes in that manner. The topological isotopy class doesn't matter, as I said. But I would sort of say that in that case, you sort of cheat. I mean, that's a cheating construction of exotica where the exotica really came from an exotica in B4 in some sense. So, does that answer the question?
Are there any questions or comments? If not, let's end hearing again.